Thank you. Can you all hear me? That's better, right? Thank you, Ms. Atomo. Welcome back, everyone, after lunch. I hope we can keep you awake in this session here. And I will talk about the evaluation of stratospheric temperature, and in particular, temperature trends in the stratosphere. And then I'm going to diverge a little bit from what I promised in my abstract, and I need to squeeze in a little bit of tropical upwelling, because that's something I've done recently, and recent stuff is always more exciting. Good. So just that we are on the same page, let's recap why we're interested in stratospheric temperature. First of all, a lot of the Earth system models use reanalysis temperature to evaluate the models. So what you see here is a plot from the ESM-VAL tool, and you see the biases in model temperature in the stratosphere relative to error interim. And you can see these biases are quite large, especially if you have a low-top model. And if you really want to understand the biases better, and if you want to see how they change over time, you need some confidence in your reanalysis temperature trend as well. And that's important. We want to get these temperatures and these temperature trends right, because they're important for the radiative CO2 forcing in the models. And we know that the upper stratospheric temperatures are also very important fingerprints for the anthropogenic impact on climate. And then we have a lot of offline models that we run in the stratosphere. We want to look at composition, especially at ozone or aerosols or water vapor, and we drive these with reanalysis. So you really want to get your temperature right in the reanalysis data set in order to have the right amount of water vapor that you bring into the stratosphere. Now, the evaluation of temperature trend, or temperatures in general, in reanalysis has been done in the past. So that was part of the SRIP project. And this is a figure from one of the papers that was published. And you see here, I've just taken two examples from this figure, two reanalysis data sets, and they're compared to HRDLS, the satellite instrument from HRDLS, which is a great instrument to compare to, a lot of things that you can deduce from this comparison. The one downside is that HRDLS is relatively short. It's 3 years long, so you can't really look at trends. And what you really want to compare to is an independent data set that is not assimilated by the reanalysis. So what's new, what I'm going to show you today, we have a new and independent data set for temperatures in the upper stratosphere. So I'm going to show you that. And then I'm going to switch and go to the lower stratosphere and go to the tropical tropopause layer where the air enters the stratosphere. And then show you some evaluations of temperature and upwelling in the lower stratosphere. Good. So this new temperature record is from the Canadian limb sounder OSIRIS. OSIRIS measures stratospheric composition, but recently we've also developed a retrieval for temperature, and that has recently been published. It covers the middle to upper stratosphere, so 35 to 60 kilometers roughly. And you see here OSIRIS in comparison with SABRE temperatures and MLS temperatures, and these are anomalies in the tropics roughly at 40 kilometers. So you see these interannual anomalies agree very well between the three satellite instruments. And then we compare OSIRIS, which is the black line, to three reanalysis data sets, ERA 5, JF55, and ERA 2. And you can see that all three reanalysis really capture these variations very well. And we sample the reanalysis like with the OSIRIS sampling pattern in order to compare really apples with apples. Good, so let's look at trends now. We've taken these time series and then calculated trends. And you see here the trends as a function of latitude and altitude. And from OSIRIS, that's the upper left. From MLS, that's the lower left. And then we sample each reanalysis with the two satellite sampling patterns. So each reanalysis has two little panels here. And well, what you see if you start with MERA 2, which is the second column, MERA 2 assimilates MLS temperature. So they show very similar trends to MLS, which is a good thing. The numbers are very reasonable. The one thing that I would like to point out is that we see in MLS, we see some vertical oscillations of the temperature trends. You might see that here. You have a maximum around 50 kilometers, another one at 40. You see it better when you look at the profile. We're pretty sure that that's retrieval artifact from the MLS temperature retrieval. So now MERA 2 shows the same oscillations because they assimilate the MLS data. Looking at ERA 5, it looks quite good below 45 to 50 kilometers, but once you come to the stratopause and go into the lower mesosphere, you see that the trends are too large, a factor of 2 or 3 too large, too much cooling in this region. And then JF55, we see also a bit too large temperature trends in that region, not quite as much as ERA 5. So to sum this up, trends are quite reasonable below 45 kilometers, and then you see larger differences above that level. All right, let's switch and go to the tropical tropopause layer. I'm going to talk about the cold point a lot, so that's where you find your coldest temperature, and we're interested in that because it sets the entry value for stratospheric water vapor. So that's quite important. And you see trends of the cold point over the last 20 years as a function of longitude and latitude, and then the observations from GPS in the upper left panel. And then we have the 3 reanalysis data sets there. And you see there's overall warming over the last 20 years. The lower stratosphere is actually warmed over the last 20 years. And there are some specific patterns, and these patterns are related to tropospheric temperature trends. And all the reanalysis really reproduce the patterns quite well. They also reproduce the seasonal cycle. I'm not going to show this here. And these anti-correlations with upper tropospheric temperature trends are reproduced as well. Good, let's go back a little further in time. So now we're looking at tropical mean averages for 1980 to 2001, that's the lower part of the figure. Then the time period that you've just seen, 2002 to 23, that's the middle part. And then the full time period is at the very top. And you see observational trends, those are the green and blue columns here. Based on the adjusted radius on data sets, GPS is black, and then you have your reanalysis in red, yellow, and purple. And that's a very nice figure that shows you very clearly how there was a shift in the temperature trend from cooling before 2000 to warming after 2000. And we see that all the reanalysis really are able to capture that shift in the temperature trend quite well. And there's an ongoing discussion in the research community, what's causing the shift in the cold point and lower stratospheric temperature trends. And one leading candidate are changes in the circulation, so dynamical changes, potentially due to the recovery of ozone that started around the year 2000. So now if we want to look at the dynamics, we can look at upwelling. We know that upwelling is directly related to the temperature at the TTL and in the lower stratosphere. So I'm showing you here, and upwelling is really hard to get from the observation. So now you only see upwelling trends from the reanalysis. And if you look at the early time period, 1980 to 2001, you see that you have an increase in upwelling. So this is Pascal per second per decade. So negative numbers means you have more upwelling. So an increase in upwelling, and that's consistent with the cooling of that region. So more vertical upward motion, you have cooling. And then if you look at the time period after 2000, that increase in upwelling now turns into a decrease or a trend around zero. And that's consistent with a change of the temperature trend to a warming over that time period. So that's quite nice. The absolute numbers are quite different of the trends. You can see that as well. But I think it's quite encouraging to see that the dynamical variables and the temperature are consistent, and they both basically show us this change of the trends around the year 2000. Now, when making this figure, I was very unhappy because it was so wide. Aesthetically, it's not nice, and it's also just not very satisfying to not have any observations. So I started looking into some satellite observations, trying to estimate upwelling from satellite observations. And I'm using here MLS water vapor. So if you have the tape recorder in the tropics, you can see this upward propagation of the minima and maxima that is set by the seasonal cycle in the cold point temperature. And if you can estimate how fast the maxima and minima go upwards, then you have your estimate of your vertical upwelling. So you basically take a time series at a lower level and then a time series at an upper level, and you shift that time series at the upper level slightly forward and always calculate your correlations between the time series. And once you have your maximum correlations, that's when you have the perfect time lag, and that time lag then allows you to calculate the upwelling. And I'm just showing that here for just 1 point in the graph. So you do that for that time when you get 1 point, and it's really an average of the upwelling over that 1 year time period. And then you do that for all the time periods, and you find this time series of tropical upwelling. And what you see here are just interannual variations in upwelling. There's no seasonal or sub-seasonal variability in this time series due to the method that we use in order to estimate this. Now, just a sanity check, is that just white noise, or is that a reasonable time series? I'm showing this here together with the cold point temperature from GPS. So it's estimated water vapor from MLS, and then temperature from GPS. And we see that we have this anti-correlation that we know should be there. It's quite large. It's minus 0.7. So that's quite a nice match. So it shows us something reasonable that we can estimate with this method here. If you have more upwelling, you have less ozone. It's also anti-correlated with ozone, by the way. We don't see that here. So you have less ozone, and then you have a warmer cold point temperature, either due to the ozone effect or due to the dynamical effect. Good, let's compare the upwelling estimate now to the upwelling in the reanalysis. And I'm taking here the SREP zonal mean data set that Patrick has put together, and I think Patrick has a post on that today, actually, if you want to learn more about it. So taking the vertical component of our stratospheric circulation and then compare it with the upwelling estimate. And these are the absolute values. I don't really want to talk about them too much because we're not comparing exactly the same quantities, but I want to talk about the interannual anomalies in these time series. So if you see your interannual anomalies in the MLS-derived upwelling, agrees quite well with the interannual anomalies in the reanalysis upwelling. And that was, well, I'm quite open about it, that was a bit of a surprise to me and to some colleagues that I showed that was a surprise as well. We were all quite excited about that because we weren't aware how well that agrees with these observational estimates. Now, once you have a bit of confidence in the upwelling from the reanalysis, you can go a step further and look at the wave driving in the reanalysis. Try and understand a little more what's driving these extreme events in the upwelling, what's driving the trend in the upwelling potentially, and therefore the trend in the stratospheric temperature. I'm using the Elias and Palm flux here, and you see I'm using two quantities of the Elias and Palm flux, the P flux, one that shows us waves that propagate meridionally in the subtropical lower stratosphere, and then the other one shows us waves that go upward in the mid and high stratosphere in the mid latitudes. And we can see, and those are the green lines in the two panels, and this is just for MERA 2, but the other reanalysis show basically the same thing. And you can see it's mostly the meridional component of the EP flux that is consistent with the upwelling, so it's mostly these waves that go into the subtropics and break there. Except for the last 3-4 years, and these last 3-4 years are quite interesting because they drive a large part of the trend. And over the last 3-4 years, from 2019 or 20 onwards, it seems it's more like this vertical component of the EP flux and the vertical propagating waves that are consistent with less upwelling and therefore warmer temperatures. All right, good. I'm on red already. Sorry, Masato, I didn't realize that. Good, just super quick, the summary, upper stratosphere. I showed you that the reanalysis agree very well in terms of interannual variations, but there are some differences with respect to the trend. And then when we go to the tropopause layer, you saw that the warming in the observations is captured by the reanalysis, the same for the tropical upwelling, and they also show us this change of the temperature trends around the year 2000. Okay, thank you very much.